Hi, everyone. I'm Bob Rogers. I'm Chief Data Scientist in the Data Center Group at Intel, and I'm extremely pleased to be here today to talk to you about work that we at Intel are doing along with our partners MemSQL and Thorn on life-altering and business-altering solutions with AI and image recognition. So the idea here is that we're going to give you an interesting overview of how AI is being applied to problems of child safety, child sexual exploitation, and how technology is being used not only to develop those capabilities, but also to accelerate how they're being deployed, and then to bring them out to the marketplace where they're having a real impact. So I'm going to be very pleased in a moment to introduce Nikita Shamgonov, the CEO of MemSQL, and Julie Cordua, CEO of Thorn. But I get to start out. Oh, here they are. Don't forget to tweet, follow them, etc. So I'll start with the introduction to the work from the Intel perspective. So when I go on stage, people always ask me, why does Intel have a chief data scientist? You're a hardware company. Hardware companies don't need data scientists. And the reason is that everything is being driven by data these days. So we really see ourselves as a data company. When you look at these various things, this is a depiction of what's in our CEO's head right now. We're thinking about autonomous vehicles. We're thinking about drones and systems that can have some kind of vision or navigational intelligence out at the edge. We're thinking about creating technology that connects the dots for different kinds of applications, healthcare, manufacturing, engineering, et cetera. And so we really see ourselves as the computing engine that sits underneath all of that and makes it possible to do. And in fact, as we've seen in the last few years, I'm sure you've heard quotes like this. Our CEO actually made this statement in a recent presentation. Data is the new oil. So it's a good analogy, partly because, like oil, you don't put oil directly in your gas tank to run your car. It actually needs to be refined. So we've all seen the graphs. There's huge amounts of data coming. Data scientists should be shouting, "Yay! This is amazing!" But because the data needs to be refined, we actually need to think about it a little bit further. We can't just assume that more data is better. So we've got another graph, looks not too dissimilar from the first graph. Does anyone want to take a guess as to what this graph represents? Anybody? Okay. It's the mass of the global landfill. So just because something is growing exponentially doesn't necessarily mean that it's creating value for us. In fact, our opportunity and our challenge is to find ways to refine in this case, the data or the material here, and separate the value from the part that's challenging. So, as Intel's chief data scientist, my role is to help Intel help you. So I think about it as my mission is to put powerful analytics in the hands of every decision maker. And the way we do that is first to work with end users, so folks like Thorn and MemSQL who are applying analytics technology to various problems and doing that refining to get value from data. We also work with partners to ensure that the software products that they have work as well as they possibly can on the hardware that's available. So when you run your code on AWS, for example. We want that code to run as well as it possibly can and get you the most performance and the most value for your cost and your effort on that infrastructure. So Intel actually has a huge army of folks who are dedicated to optimizing. And if you look at what you'll hear from MemSQL, it's a good example of how Intel wants to help everybody find ways to get the most performance. And then finally, when you think about what's coming next, the future of computing really depends on which algorithms become most important and which use cases for those algorithms are most important. And then finally, what data is driving computation most. So for example, video is the largest growing computational workload on the cloud right now. So part of my role and part of Intel's role in general is to look at that and figure out what do we need to build next so that the next generation of algorithms can handle the next generation of data. So that's the big picture for Intel, and it's in that context that we've worked with our partners in this story. So as an AI guy, there's lots of questions about good effects and bad effects, potential risks and concerns about AI. But one of the ways that I like to think about it is most of the applications that we're developing are actually augmenting humans. And you'll see that in this application that you're about to learn about. So augmenting humans comes in three main forms. One is we can give humans more access to information. And so there are times when just being able to access the information is the critical gap that helps a human do what they do better. In some case, it's really about reducing complexity. So if you're faced with a large amount of complex and potentially contradictory information, then artificial intelligence quite often can be used to distill that information down to the most salient points. The case in point would be in healthcare, where we're working with trauma centers to help them analyze the thousands of streams of data that they sometimes track and help them understand how to sift through to identify the key pieces of information to make good healthcare decisions for patients who are at risk in trauma. So there's a real opportunity to reduce complexity. And then finally, one of the examples that we're all very familiar with is allowing humans to handle scale. So information at scale. What do I mean by that? Well, a search engine is actually a nice example of that. There are billions and billions of web pages out there. There's no opportunity to read all that material and figure out what's there. If you want to find something on the internet, there is a that actually will provide you results that match the criteria that you put in. And in fact, it's AI because as you use it, it's tracking to understand whether you've been given the result that you were looking for. If you scroll down to the next page or click on a link 4 or 5 links down, it notes that. And the algorithms behind these technologies actually improve over time to increase the likelihood that you're going to get the results you want near the top of your search results. So the ability to handle scale is critical as an AI capability to augment humans. And in this example, what you'll see is that the scale is around helping humans process many, many, many images and match across large data sets of images. So since we're here at AWS reInvent, I wanted to just sort of put the whole picture from Intel's perspective together. We're very excited about the evolution of AI and the opportunity to take hardware at the edge, such as this Alexa 3D RealSense camera that acts as your eyes out at the edge, along with the other Amazon products, pulls that data into the data center and actually creates an environment in which hardware, data, and a very vibrant software ecosystem can all come together and create value around the data that's being generated both at the edge and in the data center. So we really, I think the interesting opportunity for Intel is to really work to ensure that everything works well, everything works together, and that when you're bringing data in from the edge, from your data center, everything coming together, that you really get maximal value out of that data and can do that refining as effectively as possible. So now I'm going to talk to you about work, very specifically the work that we've done with Thorn and MemSQL to create AI that can protect children. So there's a challenge that there are millions of web pages created each year that sell somebody for sex. And among those, a significant percentage that are selling children. So when law enforcement recognizes that a child is being sold, they need a way to determine, among other things, whether that child is a known missing child. So there's the National Center for Missing and Exploited Children. The National Center has a database of 40,000 images. And you'd like to be able to match the child in the photo on the web page with the 40,000 images in the missing children's database. So what we did about a year ago, we partnered with Thorn to help them tackle this problem, along with MemSQL and Microsoft and others. And what we did is we created a highly customized AI capability to recognize when the AI is being shown two images of the same child, regardless of whether that child is many years older, whether it has a different hairdo, different clothing, different lighting, makeup. And so the idea was to create this very specific capability to help address the use case that Thorn was tackling. Now, I really like that as an example of how AI works in general. So the thing that's interesting about AI from a functional point of view is that AI systems are doing things today that only humans could do 10 years ago. That's mind-boggling, right? We've been fantasizing about this, or at least old fogies like me have been fantasizing about this for decades, to have our computer systems be able to do things that humans can do, recognize cats in photographs, for example. But what's extremely interesting about the fact that we're able to create these technologies now is that they're actually being created purely by examples. That is, if I were to ask you to create AI or create an algorithm 10 years ago, I want you to write down 10 programming rules to recognize a cat in a photograph. Well, you'd look for bright light and dark spots and maybe some lines or edges. And if they did this, you'd say, oh, that's the top of a cat's ear. You'd look for another one, and there's another top of a cat's ear. And then you'd look for the little triangle nose. And that would be your algorithm for finding a cat. And we'd be like, oh, cool. We've got an algorithm to find cats in photographs. And then I'd show you a photograph of a cat looking sideways. And the thing would fail. So then we'd have to write more rules. Oh, but if it's facing sideways, then the nose is this way and there's only one ear. You can see that that blows up into a combinatorial problem. An almost uncountable number of different rules and variations you need to take into account. It's very, very hard. AI can learn from examples like this. We literally, as humans, I know that those first two kids are my oldest son. at different ages. And right below that, 2 pictures of my second oldest son. And then 2 pictures of my third oldest son. And then my fourth oldest son. And if this is a recursion, then obviously I have infinitely many sons. But actually, this is the whole set. So rather than programming rules to recognize children at different ages with different hairdos and different glasses and the whole 9 yards, I'm actually just giving it examples. That is exactly what we did here. It's what we do for voice recognition. It's what we do to tag text with AI. It's what we do for all these techniques. It's incredibly powerful because it puts us humans back in the driver's seat. We're defining the data that's then creating the capability. It's very powerful. It's very exciting. And in the case of this use case for protecting children, it gives us a very strong sense that when we get up in the morning, we're doing something wonderful. So with that, I'm going to stop, and I'm going to pass the podium over to Nikita, who will tell us how MemSQL has taken that basic AI capability and just dialed it up to 11 to run it on AWS. Nikita?
Thank you, Bob. Very cool. So I'm going to talk about kind of the last mile computation here. So what happens if you want to perform a visual search and what kind of infrastructure you want to use for that type of computation. But before that, let me introduce myself. My name is Nikita Shamganov. I'm the CEO of MemSQL. And what is MemSQL? Well, MemSQL is the database for your real-time applications. So when you want to perform your computations real-time with low latency response and high scale, that's what you use MemSQL for. And it's kind of hard to talk about databases because databases are infrastructure. And what we interact with every day is apps. And today we are all familiar with world-class, super easy-to-use apps, things like YouTube, Facebook, Pinterest, and Uber. And those apps are super simple to use, they're interactive. But the infrastructure to power those apps is incredibly complex. So I know this firsthand. I actually worked at Facebook in the past. And it's a mind-boggling amount of infrastructure that goes into powering an app like Facebook or Instagram or WhatsApp. So the typical 3 pillars of that back-end infrastructure are the data lake, all sorts of data science infrastructure, tools and libraries and compute frameworks, and then also the database, because the database stores that operational data that you use to power your application. So now here's an example of an application. Hopefully I can play this video. This is a customer of ours. The name of the customer is Nairis. And they built an app on MemSQL that allows you to take a picture of a real-world object. And then it goes and finds that image, performing real-time visual search in the massive catalog of their products. So that's how they perform real-time visual search. And similarly, Thorn uses that very same technology to combat child sexual exploitation. So we'll learn more of that later on the presentation. So how does it actually work, and what goes into building a real-time application like this? So first of all, you need to train a machine learning model, in this particular case, a deep learning model, and then applying that model to a particular image allows you to extract what's called a feature vector. You can also think about the model as a number of layers, and you perform basic algebraic operation to go from one layer to another, and that operation is dot product. So given that image, you can go layer by layer, apply that tensor or vector multiplication up until the very last layer. And what you get right there is what we're going to call a feature vector. So now imagine you have a database of images, which could be products, that could be faces, that could be whatever, frames in your video. And we extract a feature vector by applying that model to each image. Then we take that and store it in a database in a relational form. How many people know SQL? Yeah, a lot of people know SQL. So it's pretty simple. We create a table. We have an identifier for each feature vector, and then we have the actual feature vector that's stored in that table. So now let's understand dot product. It's a basic arithmetic operation, and it just so happens, based on a lot of research and the properties of the machine learning model, that the dot product of a feature vector of an incoming image and the image that's stored in the database gives you a similarity score. And the closer that similarity score to 1, the more similar are the images. So now we can take that concept and then we operationalize it in a database where we say, OK, given an image, then you apply a machine learning model. You have the feature vector. Now you need to find all the images that are similar to this and order them by the similarity score. And that SQL command that's right there on the slide will give you the answer to this question in just a few milliseconds. So now let's talk about how we implemented dot product. There is a technology in Intel processors that's called SIMD. That technology is not necessarily new. It stands for single instructional multiple data. What is new, though, is that Intel keeps making it better. Generation after the generation of each CPU, you can perform quote-unquote vectorized operations on larger quantities of data. So AVX512, as in the name, allows you to perform a vectorized operation on 512 bits, which is the same as 8 64-bit integers. So here's just an example of how we can add in one instruction, how we can simultaneously add 8 integers. So why is it important for dot product? Well, dot product is a very basic formula. So now you can implement dot product in a vectorized fashion. The interesting point here is that computation, the dot product computation, is so fast that when you evaluate this over a large quantity of data, your bottleneck is not compute anymore. Who would guess what the bottleneck is in this particular case? Yes. The bottleneck is memory bandwidth. So memory bandwidth is about 60 gigabytes per second. And with basically with a CPU that can run on the laptop, on this very laptop that I'm driving my presentation from, you can perform that computation at the memory bandwidth speed, which gives you that insight that for training the model, when you perform a lot of operations, a lot of matrix and tensor operations, you actually need custom hardware. Things like GPUs, and Intel comes up with a whole bunch of products that allow you to speed up those computations. For operationalizing the model, you can do it anywhere. You can do it on the laptop, you can do it in the data center, and certainly with MemSQL, you can scale that computation out and run this computation on a cluster. So we didn't stop there at image recognition when we implemented vectorized technology. We actually took it and propagated all the way through. So now every SQL command that you run on MemSQL leverages that vectorization. And for a typical analytical query like this that you have on the screen, you can process data at massive speeds. And by massive speeds, I mean you can go up to 100 billion rows per second processing that data. And that comes from certainly hardware accelerations and the fact that at MemSQL we can scale your computation out. And if you have a bottleneck and that bottleneck is compute, you can always increase the amount of compute by giving MemSQL more nodes and fundamentally more cores. So the gist of my presentation is We're super excited to be partnering with Intel. We're excited by aligning our roadmap with the hardware innovation that's coming out of that company. And together, that allows you to build new class of applications, those real-time computation applications that can perform a tremendous amount of compute per interaction, right? So we have demonstrated that you make one interaction by taking a picture, and then you drive an enormous amount of compute, and you do it just in a few milliseconds to drive kind of real-time results. So now I'm going to pass it over to Julie, who's going to talk about the real-world impact of this technology.
Thank you.
There you go.
All right, thank you. I'm Julie Cordua. I'm the CEO of a nonprofit called Thorn. I will ask if it's okay if you not take pictures of my slides. There's a few in here that are sensitive, so if possible, I'd like to not have those be distributed. We are a nonprofit that builds technology to defend children from sexual abuse. What I'll be talking about today is actually work we've done with MemSQL and Intel specifically on our focus to help find missing and exploited children who are sold into sex trafficking in the United States. Just to give you an idea of that, we were started 5 years ago, and we were looking at the intersection of technology and child sexual abuse. Obviously, we know the internet didn't create child sexual abuse, but it definitely democratized it. So we have dozens of online marketplaces today where people are bought and sold for sex, and somewhere in there are children. And it's very difficult to figure out which ones are children and which ones are not. We have tens of millions of images and videos circulated every single day of child sexual abuse material, or legally known as child pornography. We have live streaming abuse events occurring every minute, every hour around the world. And we were formed as a way to create a counterforce to that. It was clear that predators had overtaken all the great innovation that many of you have been a part of developing, and we wanted the best and brightest minds to be a part of being a counterforce to that as well. So when we looked at child sex trafficking in the United States, we kind of dove into the issue. We talked to victims. What we knew and what we heard from children who'd been removed from sex trafficking situations was 3/4 of them were sold online at some point in their sex trafficking experience. Oftentimes, they were forced to write their own ads. They included fake names, fake ages, sometimes fake pictures, but many times an actual picture of themselves. We went then and looked at the marketplaces. Over the last several years that we've been doing this work, the volume has grown from over 100,000 escort ads posted every day to over 150,000 escort ads posted every day in the US. And we went and talked to law enforcement, and we said, how do you focus, right? So there's no way they're going to arrest their way out of this. Their mission for those who work on sex trafficking is to find the most vulnerable victims, and that means focusing on children. And when you're dealing with a marketplace that most of your information is false, how do you know what is a child? And so we undertook an experiment about 3.5 years ago using natural language processing and some machine learning to say, could we train algorithms to basically read escort ads and predict which ad was most likely a child? We can't tell you it's a child, but we can say maybe of the 150,000 ads today, you should focus on these 100, and you'll more likely find a child. We were successful in doing that. We built off of that experiment and added some other algorithms to that, and built a tool called Spotlight, which is available today. Today it's used by over 5,500 law enforcement agents and 1,300 law enforcement agencies, and has helped identify over 20,000 victims of trafficking, 6,000 of which are children. We ingest all the information from the internet, and then you can see up there, we add in flags for officers where we tell them this ad looks like there are signs of control or signs of immaturity. You should focus here. They can sort by their jurisdiction, by different risk factors, and surface up ads that are most likely ads of relevance to them. This ad in particular says she was 18. This is a real ad. She was a 15-year-old who had been taken by someone who had posed as a 17-year-old, turned out to be a 35-year-old sex trafficker who was selling her within 48 hours of meeting her. And she was rescued within 48 hours of officers looking for her because the ad was flagged as a minor, and they focused on that ad. Today, our operation, the data that powers the tool is about 140 million ads, 33 million unique images, and 3 million unique phone numbers that we are constantly trying to draw connections between and elicit insights from. I already covered this, and operating across the US and Canada. When we met MemSQL and Intel, we were looking to take on the next step of this tool to say, okay, let's start intersecting a new set of data. Right now, we're just looking online in the escort environments and trying to draw predictions on this data. We know that the majority of children trafficked in the United States are coming out of the foster care system or are runaways. They're not all reported missing, but some are reported missing. So we talked to the National Center for Missing and Exploited Children. They have over 20,000 cases of missing children. 90% of those are endangered runaways each year. And 1 of 6 endangered runaways in the US are likely sex trafficking victims. And just in the past 12 months, a new law was instituted that any child who runs from foster care goes immediately into the National Center's database for likely trafficked children, because the likelihood that they will end up for sale online is incredibly high. So we met MemSQL and Intel, and we said, we have pictures of all these kids who are very likely online for sale. Can we start to match the images? Because all of our intelligence in the first version of our tool was text-based. Could we start to match these images and add another layer of intelligence to the tool? And it was just about taking the images of missing children and matching to what we're seeing on these escort services. So what we built together is this platform where you can surface potential matches and then allow investigators to basically tell you you're right or you're wrong, this is interesting, and kind of train it over time. The work that Intel was talking about with age regression is incredibly important because you may have images of a child from a few years ago, and also when a child goes missing, the picture that you're looking at is a school picture, something their family had. The picture that you're looking online when they're being sold, they're wearing makeup, they're in a dark room. How are you going to match these two images? So that was a lot of the training that we've done with Intel and MemSQL. I'm not going to get into all how this is built, one, because I don't necessarily understand every single part of this. But what we've done with MemSQL is incredibly important. The processing time when we took the first pass at this was, I mean, we'd sit there and just watch it run and hopefully something would come out. We needed to go a lot faster than that. So the idea of ingesting images real time as we're bringing them in, and we bring them in every hour, we're capturing that vector, and we're able to store that, and then as new images come in, being able to run it and seeing if we're getting matches that are happening each day. The idea is actually to build a pipeline so that we can plug in different facial recognition tools and see what is best as we evolve and grow over time. So we started with VGG face, and now moved on to FaceNet. You can see with incredibly improved results. We still have a way to go, but I think good enough that we will be putting it into production very soon. I think what's most interesting is if you can actually see this live and what the impact would mean. So just to give you a sense of how this work is actually done every day. So there are analysts at the National Center for Missing and Exploited Children who, when a child is reported missing, they literally take that image and they go onto these escort pages and they open every link of every ad and look at every image with their eyes and see if they can find a match. That is not scalable. That does not mean you are going to find a kid quickly. So we can show you what a difference this will make, and this requires audience participation. So I'm going to need some help. So we're going to do this first by ourselves, like the analysts at the National Center for Missing and Exploited Children do. This child, tell me which picture is her. Anyone? Anyone? Not that one? Far right at the top. There we go. All right, let's do it again. Oh, this didn't change. Well, we know that's not a match. I'm going to skip that level. Here we go, level 3. All right, let's find him. There? No? There? The first one? No. Have I missed him? Wearing the tie? Go up? Am I supposed to go up? Oh, this one? Left of the tie. Left of the tie. Right there in the middle? All right, we still haven't found him. Time is ticking. We're just going to click them all until we...
There he is.
There we go. All right, we're going to do the same thing with the system running in the background. It's not that difficult. And it's pretty obvious the time. So the system right now, I mean, we're training off of, we actually are training off of real data, but originally we trained off of celebrity data because we didn't have age-progressed photos. So this is just an example, but it's a real life example because an analyst gets a report of a child gone missing and they sit there in that frustration looking and looking and looking. And right now what the system will do is basically serve up and say, here's your 10 most likely, and most likely that person, if they are online and available in a public forum, we will find them and they will be found. So thank you.
Thanks, Julie and Nikita. So I think we have time for some questions. And so we would love to hear any of your questions. Anybody? Okay, yes, question here. So the question is, how is the MemSQL work integrated with AWS? Oh yeah, hardware. So do you want to talk about the hardware behind what you're doing on AWS?
Well, yeah, sure. So the way it's integrated with AWS is there's a lot of Intel CPUs on AWS to spin up a virtual machine, and then there's a processor there. And chances are the processor either supports AVX 512 or the previous version of AVX, which is called AVX 2.
So it's literally just the Xeon server processors. We've got a question in the back there. So the question is, have we done something specific in the network architecture for the deep learning to create this ability to recognize a child over different ages, or is it just purely in the training? And the answer is it's actually purely in the training. Literally, we start with a, Julie mentioned VGG face and FaceNet. We start with a generic facial recognition capability. It's an architecture that was actually optimized to recognize adult faces. And then we re-optimize it with this ever-growing data set that we're building as a part of this work to give it children the same image of the same child at different ages, different hair, and so it ends up being purely the training data, which I think is a really, really important point about AI in general, is that, as I was saying, the examples, the data that you give really determines the behavior that you get. So when we put thought into what examples we give, we end up with very specific capabilities. And in fact, quite often you don't even have to create the entire deep learning system from scratch. You may start with a basic capability and then optimize it for your specific problem on your specific data to get a customized result. In fact, that's one of my favorite ways of getting AI results. Sometimes people refer to that as transfer learning, but it's very, very powerful. Yeah, question over here.
Yeah, I wonder if you could talk a little bit about how the three of you came to work together.
Yeah.
It sounds like there's probably a story there.
Yeah, so how did the three of us come to work together? So I have my version, but I'd like to hear your versions, and then I'll throw in my 2 cents.
Well, I'll just start with this type of partnership is fundamental to our nonprofit. So we're a small team, but we do have our own engineering and product team. But, and we run 2 products that run in 23 countries. This is just one of them. But we can't, as a nonprofit, like I'm never going to be an expert in AI and facial recognition and speedy databases and all of this. So AWS is also one of our big corporate partners. So we look for corporate partners to come in and augment our ability. And actually, one of our volunteers is at Microsoft, and he was helping us with facial recognition 2 years ago. And I think he was friends with you or someone on your team.
Yeah, we have a team in Seattle. Quick plug, we're hiring. Thorn hosted the hackathon.
Yeah.
And a fella who was previously at Microsoft, now working at MemSQL, went to the hackathon, brought some of the folks on the engineering team, and they participated in the hackathon. And they're like, oh, I bet we can do it 1,000 times faster. And then they ran, so out of the box, we couldn't deliver on those capabilities. But then they spent a weekend, and by the end of that weekend, we were.
And I would say it was similar with Intel in that, and if I can say this, I'm going to. But for both of them, when we met both of them were working on new features and new technologies that they wanted a test case for. We're a great guinea pig. And so we, obviously signed relationship agreements with them and stuff, but they were able to train and build out these new features that they then go sell to their customers. But we're a great proof point for it, and oh, by the way, we've got this huge benefit out of it. So I think that's when we met you guys also, that was the first phone call we had was, hey, a year from now, we're going to be introducing this new, chips, or I don't have all the right language, but we think we can be really helpful to you. And then this all came together on this one specific project. And I think as a nonprofit, actually, I would say we are unique in that we do have a product and engineering team, so we're not looking for our partners to do the heavy lifting. They can plug in to a team that's already operating and products are already up and running and kind of help us go the extra mile and do the things that we can't do in-house.
One follow-up. So initially, before the three of you got together, did Thorn have that manual workflow product, without the AI assist?
On facial recognition?
Yeah.
We were not doing any facial recognition before we started this project.
So law enforcement.
All of a sudden your users got facial assist.
So you had Spotlight, which
Yes.
was, so they had a tool that was text-based that was recognizing when children were being sold. And law enforcement would take that and they would, by hook or by crook, usually in contacting the National Center, try to do this match manually. So that was really the pain point. How do we scale that? Because we saw that the largest data set that Julie searched just now was 100 images. So scaling that to 40,000 was just not, it was not something that was going to happen at scale for all these users of it. So yeah, it was very exciting. And actually, for my part, I want to throw out a couple of props two colleagues of mine at Intel, Lisa Thea and Lisa Davis, actually came to me about a year ago and said, hey, we think there's some pretty interesting ways to use technology to help fight child trafficking and help with missing children. And so we investigated and found that we were able to work with the National Center directly, and then also with Thorn with this amazing use case. And that, just to talk about Thorn as a partner, they really focus us on the problem that we need to solve to do something meaningful. So we're not casting about trying to figure out, what is it that we should do? We've got this cool technology, let's hammer some nails with it. They actually know exactly what needs to be done, and they can pull in the right partners, and it's just been quite an incredible journey to work with them. And of course, to see it just screaming at Mach 1 speed on AWS is pretty fascinating as well. It's quite compelling. More questions? Yes?
So obviously there is still one level of human intervention. AI makes it easier. A human clicks yes. Do you see that moving forward, entirely automated? And how do you benchmark something for when you say that it is really ready for use?
Yeah. Okay, so the question is, right now we're augmenting a human who is making the final decision. Do we see a full automation in the future, and how do we benchmark whether something is acceptable? So I'm going to let Julie, I have my own opinion, I'll let Julie answer also around when, if ever, you would automate. As I said, I'm a big fan of augmenting humans. In our work for the National Center for Missing and Exploited Children, they have an interesting problem in which they receive about 15 million reports of child abuse and child pornography on the internet. And we've built a machine learning pipeline that can compress all of they basically, a year ago, they had about a 30-day backlog in cases that their analysts had to review. And what we did for them is we created machine learning that allows them to recognize where every single report needs to be sent. And it can all be done within 24 hours. And what they do is they control based on what's coming in and what those cases look like, because there's a vast variety of different kinds of situations. There's a child who's in imminent danger, and there's an image that's been cropping up on the internet for 10 years. Those are vastly different in terms of the speed that you need to respond. So we give them the control in whether they automate disposition of any of those reports, and if so, based on what criteria. And I think that's very powerful, because as a technology provider, we can say, we measured the precision and recall to be 98% and 99%, but that doesn't tell you whether it's doing what it needs to do for the user. So now I'm going to let Julie answer the real answer.
No, I would agree with that. I mean, I think in this field, there's a spectrum. There's millions of abuse images, and this is different than trafficking, child sexual abuse images that have been seen millions of times, and if they're seen, you could pretty much automate that. You can say, I see it, this is bad, we know it, get it off, right? Or just move it over here. When we're talking about, there's another thing. If the child in that image has already been identified and rescued, just clear the content. If the child, we're talking about children's lives here, so to fully automate that would be incredibly difficult. Like, you always need to put eyeballs on those images and know, and also even in Spotlight, when we surface up, focus here, we don't take away everything else. We give officers the freedom to just go look at everything. We're just gonna point them to a certain direction to help them be better at the work that they're doing. Because, I mean, if you got into a fully automated situation and your algorithm wasn't as finely tuned and you're missing kids over here, that's a bad situation to be in.
Exactly.
Yeah,
Well
I kind of want to summarize. It's really, technology is there, right? We can do a lot of things with the technology, but it's what you want to do with the technology really defines if it's going to be fully automated or there's going to be human interaction in it. In this particular case, right, the action is sending a SWAT team to rescue a missing child, right? So since the operation is very physical in nature, it's a very real-world type situation, then it's okay to have some eyeballs, looking at the at the recommendation of the system before you actually dispatch the SWAT team. Now, if you control the whole pipeline, like YouTube these days, for example, people uploading a video, that's where you can make an automatic decision. And you can say, hey, look, this video does not conform to whatever rules you enforce, and you do not allow that video on the system. So really, it depends what you want to do.
That's a great example. Other question? Anybody? Well, thank you for being here. Certainly, it's been a huge highlight of my career to work with Thorn and MemSQL on this work, and it's wonderful to be able to share it with all of you. Thank you.
Thank you.